So this was our first step, that we got the thermodynamic probability of the distinguishable particles in terms of the energy levels. Now let us look at the WIT. Now let's find out thermodynamic probability for the indistinguishable particles. Let's take a very simple system where we have two particles and my energy state is threefold degenerate. So I have two particles and my energy state is threefold degenerate. So what are the different ways I can distribute these two particles? So threefold degenerate, so I said, so I have energy level 1, 2 and 3, so 3 energy levels, and I can put both the particles in this level 1. I can distribute these two particles like this also. I can put these two particles in here as well. I also can put them one here, one there. I can put one here, one there, and I also can put one here, one there. So I do have 6 different ways of distributing two indistinguishable particles in an energy state having threefold degeneracy. So in other words, I have 6 microstates. So if we go back to our previous discussion of distinguishable particles, what was the possibility? How many number of microstate we could get if the particles were distinguishable? So let us see. So if our particles were P and Q, so we can distinguish the particles as P and Q, and we had threefold degeneracy. So I could keep here, I could keep both of them here, I could keep like this, I could put like this, I could put like this, rather I put, I'm sorry, I put Q here, I put P here, Q here, and I put P here, Q here. But we have 3 more possibilities where I can exchange P and Q. So here we got 9 microstates. And that was a problem, perhaps. That was a problem due to which we came across the Gibbs paradox. So when the particles are not distinguishable, which is the case in practice, we get 6 microstates for this simple example of 2 particles distributed in an energy state with threefold degeneracy. So now for this particular system where so where we have okay, we have 2 particles. Let me redraw this again. This is very important to understand. So basically I am redrawing the energy state with threefold degeneracy, in which 2 particles are distributed. So one distribution was this, another distribution was that, another was that, one was this, another was here, and another was here. So these are the 6 possible microstates we came across. Now, how can we write this in formula? So if we want to find out the thermodynamic probability for this particular state in terms of energy level, what you can write is this. So this is thermodynamic probability for this particular state. We can write, so here we had number of particle was 2. So WL we can write as 2 factorial. How many partitions we had? We had 3-fold degeneracy, and for the 3-fold degeneracy we had to give 2 partition, 1 partition here, 1 partition there. So we can write 2 factorial, and at the top we write this plus this, 2 plus 2 factorial. And if you find it out, so this is basically 4 factorial divided by 2 factorial and 2 factorial, which is nothing but 4 cross 3 cross 2 cross 1 divided by 2 cross 1 cross 2 cross 1. So which is 6, and this is the 6 number of microstates which we got. So it matches, right? But this expression what we have written, can we generalize that? Yes, we can generalize that, and the way we can generalize, so here my 2 was the number of particles, which is NL in that particular energy level. So we can write NL factorial. The second term we said this is the number of partitions. Here it is 2 because it was 3-fold degenerate. So if my degeneracy was GL, so my number of partitions required is GL minus 1 factorial. So where GL minus 1 is nothing but the number of partitions, and on the top we can write 2 plus 2 as we written. So NL number of particles plus GL minus 1 factorial. So this is the thermodynamic probability for that particular state in terms of energy levels. Okay, now let's simplify this expression of WL. So we got WL, thermodynamic probability for a particular energy state, but in terms of the energy levels is NL plus GL minus 1 factorial divided by NL factorial and GL minus 1 factorial. This is the WL, small WL. Now let's simplify. So how we can simplify? We can expand the numerator, and if we expand, we'll get NL plus GL minus 1. We get NL plus GL minus 2. We get NL plus GL minus 3 plus this series goes on. This series goes on with this number keeps increasing, and at certain point this number becomes equal to NL, and at that point, so NL minus NL goes off and we get GL. But the number continues. After that we get GL minus 1, we get GL minus 2, then we get GL minus 3, and it goes on. And at the bottom we have NL factorial, GL minus 1 factorial. Okay, so the above expression we can rewrite as NL plus GL minus 1, NL plus GL minus 2, NL plus GL minus 3 plus GL. And now look at this term. So we have GL minus 1, GL minus 2, GL minus 3, and the series goes on. So therefore, this series is nothing but GL minus 1 factorial. Is that not right? Yes. And therefore, that GL minus 1 factorial can be cut from both numerator and denominator. So what we get is NL plus GL minus 1, NL plus GL minus 2, NL plus GL minus 3 plus series goes on till GL divided by NL factorial alone. Okay, now if you see on each term above, you see each term has a GL. So this GL term I can take out. I can take this GL term out from each of these terms, and since we have NL number of terms, I can get GL to the power NL getting out from the total product at the top. So therefore, we are writing. Let me write it down simply. So we had NL plus GL minus 1, NL plus GL minus 2, NL plus GL minus 3, GL divided by NL factorial. So as I said that I can take out GL from each of these terms, from each of the terms above, so I get GL to the power NL. Okay, let me simplify a little further before I go to make it more clear. So, so if I take GL one out from each of them, so I can write 1 plus NL minus 1 by GL. So that gives you GL and plus NL minus 1. Then we can have a GL here, and we can have 1 plus NL minus 2 by GL. Similarly for the third term, and then I get GL NL factorial. So basically I get G, so if I take all the terms out, I get GL to the power NL, and then I get basically 1 plus NL minus 1 by GL, 1 plus NL minus 2 by GL until I get just 1 divided by NL factorial. Okay, so what I have done simply here, I just taken GL term out from each of them. So when I take GL out, so from first term you get GL1 and GL goes off, so it gives you NL minus 1, likewise 1 plus NL minus 2 and so on and so forth. So you take this GL, on all the GLs in the series until you get the last GL. So if you put them together, you get GL to the power NL. And now what is remaining in bracket is 1 plus NL minus 1 GL, 1 plus NL minus 2 by GL till 1. Now since degeneracy GL is much bigger than NL minus 1 or NL minus 2 or NL minus 3, so we can neglect these terms, because GL the degeneracy in practice, if you do in the quantum states, the each of the state is 10 to the power n fold degenerate. So since the number of degenerates is much higher than the number of particles, so this term NL minus 1 by GL or the other terms NL minus 2 by GL and so on, they contribute very negligibly. So with that assumption, we can write WL as GL NL divided by NL factorial. So in other words, we write WL GL NL divided by NL factorial is what we get for the thermodynamic probability of a particular energy state. Now if we want to get capital W, we need to get the product over all the energy states and their energy levels, and therefore we take the product over WL, and that gives us the expression of WD as GL NL divided by NL factorial. So that this is our expression for WID, thermodynamic probability for the indistinguishable particles in terms of energy levels is equal to product over all energy levels GL to the power NL divided by NL factorial. And what was our WD? Our WD, the thermodynamic probability for the distinguishable particles, was WD is equal to N factorial, and then the rest of the remaining part is same, NL factorial.